Yeah, welcome again. In the previous video, we ended at the embedded firmware development language options. All right. So we're going to be continuing here. So we have several language options that we can use in our journey to embedded firmware development design. Each of them has advantages and disadvantages. So the very first one is the assembly language. And then we have the high-level language option. So in the high-level language option, we can have a subset of C that is called the embedded C, or a subset of C++ that is called the embedded C++, and any other high-level language that supports cross-compiler operations. Okay, you have the micro what is it called? You have Python. You have Python that you can use. I think you have also PHP that you can use with PHP board and so on and so forth. So there are other high-level languages that you can as well use in development of embedded systems. Okay, but C has the highest market patronage. Okay, then thirdly, you can have a mixture of assembly and high-level language. For instance, you can mix high-level language like C with assembly code, or mixing assembly code with high-level language like C. Both sounds the same thing, right? That's number one. Number two sounds like the same thing. Okay? Alright. It sounds like this. They sound like the same thing, isn't it? But you will notice that when you see mixing this with this, it means that in each of them, one is taking the highest chunk of the code. For instance, when we say mixing high-level language like C with assembly, it means that the high-level language like C has the dominance, all right, and then you put some assembly codes inside of it, and vice versa. Then number four, we have the inline assembly. Okay. All right. So next is we'll begin to talk about each of them. So we look at the assembly language first. Okay. The assembly language is the human readable notation of machine language. Okay. And machine language is the processor understandable language, what the processor understands. Okay. It is a binary representation and it consists of zeros and one. Okay. Assembly language and machine languages are processor or controller dependent. Please note this: they are processor dependent. Now, what it means is that the assembly that you write for Atmel controller will definitely not be the same for what you write with Atmega controller. All right. So what it means is that if you really want to major in writing assembly language, that means you are going to know everything about each and every controller you want to be using in your project. Okay, so that is it. So what we're saying is that it is processor dependent. It is processor and controller dependent. All right. An assembly language program written for one processor or controller family will not work with others. We won't work with other assembly language family. All right. Assembly language programming is the process of writing processor-specific machine code in mnemonic form. Please note this: it comes in mnemonic form. In other words, it is in between human and machine. Trying to give machines things that look like mnemonics. All right, you don't really. It doesn't have a peculiar human approach to understanding each and every one of them. Okay, unless you are knowledgeable in that area, you will not be able to understand the code. Okay. So the general format of an assembly language instruction is that there's going to be an opcode followed by the operands. Now there are two things: opcode followed by the operand. All right. Now the opcode, the opcode will tell us. The opcode tells the processor or controller what to do. All right, and the operands provides the data. In other words, the opcode is the instruction of what to do, and the operands will be the data, all right, and information required to perform the action specified by the opcode. It's not necessary that all opcode should have operands following them anyway. All right, some of the opcode implicitly contains the operand, and in such situation, no operand is required. Okay, so the operand may be a single operand or dual operand or more. Okay, so when we look at this example, that is written here, and this is actually for 8051 assembly. It says move A 30. Now, what does that mean? It says move the decimal value 30 to 8051. Excuse me, note this, to 8051, because this particular instruction is 8051 instruction. So when you come to 8051, there is the accumulator register designated as A. Okay, that's why we said you need to, if you want to write this, you need to know the internal makeup of that. If you want to write assembly, you need to know the internal makeup of the controller you want to write about, right? You need to have the knowledge of it before you begin to write. So you need to know different registers so you can actually refer to those registers. Okay, so here move A is the opcode, the instruction you are giving, and then that instruction, what is the data that is going to be carried out to do that? It is 30, which is the operand, the single operand is the data. All right, so the same instruction now, when you look at this, you discover that you can say move A 30. Now, this is what you understand as human, but what the machine understands as machine is the machine language, which looks like just 001, 0101, and so on and so forth. Now, when you look at this, the very first one is the instruction, which is the move A. Okay, and then the second one now, the operand. This is the opcode, and this is the operand. Okay, so but this is machine language. All right, okay, so that's assembly language for you. Okay, let's go to the next slide. So assembly language instruction are written one per line. That's one of the things you need to know. They are written one per line. So you write one for each line. You just write one. You just write another one, number two, and so on and so forth. So a machine code program consists of a sequence of assembly language instructions where each statement contains a mnemonic. I've mentioned this. We'll have the opcode, and then you have the operand. Each line of an assembly language program is split into 4 fields. Okay, so but not all fields that must be there, right? Number one is that you have the label, then you have the opcode, you have the operand, and then you have comments. And the comments are human readables, which the program will not compile. All right, so label is an optional field. All right, a label is an identifier used extensively in programs to reduce the reliance on programmers for remembering where data or code is located. Okay, so it's actually an ID, an identifier that shows you where this particular code is located. All right. Now, label is commonly used for representing one, the memory location, address of a program, the subroutine, code portion, etc. It's used to actually locate a program you want to call where it is located. Now, it is used to represent the maximum length of a label. The maximum length of a label. All right. And one of the things is that it differs between assemblers. All right. So an assembly language instructions, I think I've said that it's written 1 per line. Okay, I've said that. Okay. Now when you come down, we say assemblers insist on strict formats for labeling. All right. Labels are always suffixed by a colon and begin with a valid character. Now, when we say that when you write a label, what happens is that the next to the label, you are going to have a colon. For instance, here you find delay, which is a label, and then you find colon. Then the next, you are going to find the opcode, and then you have your comma. Then the next is that you're going to have your operand, all right? And then the next is that you are going to have your comment. Hope that makes sense. Okay, so this is an example. Then another example is like this. Okay, this actually is a delay routine that is written. Okay, now labels are always suffixed by a colon and begins with a valid character. Labels can contain numbers from 0 to 9 and special character underscore. All right. So this particular thing, this particular code written in assembly is actually a subroutine for generating delay. All right. The delay parameters are passed through the register R1. Okay. And the return value, none. Registers used in this are register what? The registers used in this are registers R0 and R1. So look at this register R0 and then look at it R1. So this thing is decrement and jump, all right? Decrement R1 and loop until R1 equals 0. Okay, then return to calling the program. What happens is that it decrements the value of this, and in the process of decrementing it, for instance, let me just say you have to count from 0 to 9. I'm giving an example. 0, 1, 2, 3, 4, 5 to 9, and then by the process of doing this counting, and when we say decrement, it's actually coming this way instead of that way. So decrement. Now, in the process of doing this counting, it is waiting. There's a time delay in the process. So when it finishes it, this instruction says return to program. So that is how you actually create a subroutine. Create a routine that you can use to generate delay. All right. So next, we look at the process of generating source file, creating hex file from the source file. So call it source file to hex file translation. So in your source file, you will have files that are .asm, and this thing is assembly and .asm. So you may have several source files, and each of them will have to be assembled as a module. All right. And when this assembler operates on the source file, it will create an object file. All right. To create an object file. But this particular object file is not what you actually convert. This object file flows into the linker and locator, which combines it together now to create an absolute object file. So the object to hex converter now operates on this and then creates an hex file. All right. Of course, there is an input of the libraries in it. So the assembly language program written in assembly code is usually saved as .asm file or .src, meaning source file, or a format supported by the assembler. Okay, so similar to C and other high-level language programming, it is possible to have multiple sources of file that you call module in assembly language programming, just like I've said in the blocks, in these two blocks now, block 1 and block 2. All right. Okay, so each module is represented by .asm or .src file, or the assembler supported file format similar to .c file in C programming. The software utility called assembler performs the translation of assembly code to machine code. All right. There's the assembler that performs the translation of assembly code to machine code. The assemblers for different family of target machines are different. You must know this. All right. A51 macro assembler from Care Software is a popular assembler for the 8051 family of microcontrollers. I think I've mentioned Care Software before. All right. So each source file can be assembled separately to examine the syntax errors and incorrect assembly instructions. Assembling of each source file generates a corresponding object file, just like in the diagram that you're seeing. We have the object file 1 and the object file 2. Okay, the object file does not contain the absolute address of where the generated code needs to be placed. All right. It doesn't contain the absolute address of the program memory. All right. The software program that is now called the linker or locator is responsible for assigning absolute address to object files during the linking process. Okay. The absolute object file created from the object files corresponding to different source code modules contain information about the address where each instruction needs to be placed in the program memory. Okay, so we are talking about this absolute object file. It has the address, the address where each of those are supposed to be in the program memory. So then at that point, a software utility that is called the object to hex file converter will now translate the absolute object file to corresponding hex binary file, and it is this hex binary file now that you now finally dump into the program memory. Okay, all right. So next we look at the advantages of assembly code. The advantages of assembly code. Okay, number one is that there's efficient code memory and data memory usage. So that amounts to memory optimization. You're able to use your memory very well. And why is this possible? It is because the programmer understands the architecture of the processor. He knows where the registers are, the capacity of the registers, and so on, and even how to get at the registers. All right. Now, because of this, there is high performance because there is effective assembly coding, and this is because the programmer understands the memory issue, the memory composition of the system is trying to design, or the microcontroller is working on. Okay. Now there is the low level access. So at this point in time, you discover that because of this, the programmer touches the heart of the hardware. it goes direct, it relates with them, and the heart of the hardware are the registers, the kernel, the drivers, the load interrupt routine. All of these things are touched at the hardware level. It's able to get at the hardware level at this point in time. All right. Now, another advantage is the code reverse engineering. Now, what this means is understanding the technology behind a product by extracting the information from the product, finished products. So when you understand how something works, you can actually go back into understanding what what went through before the finished product came. All right, because you have known the pathway that you can follow, you can navigate to get at that particular product. Okay, so there's efficient code. We say that efficient code memory and data memory usage. It is because the developer is well aware of the target processor architecture and memory organization, so optimized code can be written. Okay, this will lead to less utilization of code memory and efficient utilization of data memory. So the higher performances are gotten because optimized codes are written, not optimized codes are written, and it improves the code memory usage, but also improves, not just that improves it, but also improves the total system performance, and so on and so forth. Okay, that's the advantages, but it has some disadvantages. So when you look at the advantages and the disadvantage, you know which one to actually go and embrace. Okay, next you look at the disadvantages. Number one disadvantage is high development time. The high development time. Now, what is it that makes for the high development time? You see that the developer will take a lot of time to study about architecture, the memory organization, addressing modes and instruction set of a target processor or a controller you want to use. For instance, if you've been very familiar with using ATmega controllers, you discover that the moment you switch over to another family of controllers, that you are going to, it will be as if you are going to start learning it all over again. All right, and because of that, the time it will take you for the development will really be a long one, right? So more lines of assembly code are also required for performing a simple action, because we see how the instructions are written of code plus operand and so on and so forth. So more lines of code are written in the assembly language. Now, there's developer dependency. What it means is that there's no common written rule for developing assembly language-based applications. There's no common rule. In other words, you may find it difficult to debug a program that another developer writes, because there's no standard that was used in writing it. Right? The only thing is for you to understand what you want to do, understand the memory architecture and everything, and then you can switch into writing. Okay. Then the next disadvantage is that it is non-portable. It is non-portable. Target application written in assembly instructions are valid only for the particular family of processors and cannot be reused for another target processor or controllers. All right. So what if you just like we say, the high development time, it takes you to study it. You know why? Because each vendor has their memory organization and architecture written in different, design in different form. All right. So what you wrote for ATmega controller will not be ported. It's not easy to port it now to another controller. All right. So if the target processor or controller changes, a complete rewriting of the application using assembly language for new target processor or controller is required. All right. So if you may have a socket that we take two different family of controllers. Now, the moment you pull out the socket, the one controller, and you place another controller, you cannot port, you cannot dump into the same controller the same assembly language that you used in the previous controller. You have to start rewriting it again. Okay. So next, we look at the And yes, we look at the high level language approach. So we see the process of source file to X file translation in high level language. All right. The embedded firmware is written in any high level language like C or C++. All right. So the software utility called cross compiler converts the high level language to a target processor specific machine code. So one of the things that is very important in this area now is this cross compiler. All right. So what we are saying is that this cross compiler will have the knowledge of the target machine, machine or controller machine code. All right. It has the knowledge of it. So it converts the high level language code that you wrote into the specific target machine controller. So even when you are developing this, you are going to, in the IDE that you'll be using to develop this, before you start writing your code, you will first of all select the particular processor that you are writing. All right. And there could be header files that you need to, the library files that you will need to actually use to indicate that I am actually writing for this particular controller. All right. So the cross compilation of each module generates a corresponding object file. Right. The object file, just like in previous talking about assembly source file to X file translation, the object file does not contain the absolute address or where the generated code needs to be placed on the program memory. All right. So the software called the linker again. Now when you look at the other one, what you have at this point is simply the assembler. That is the module assembler that assembles the module for this particular source file. All right. So that's what you have here. But here you have cross compiler. All right. So the software utility, this assembler and the cross compiler does the same thing. They convert their codes to object file. All right. So and then from this place now to this place is the same thing with the other one. All right. So the software program called the linker or the locator is responsible for assigning absolute address to object files during the linking process. So the absolute object file created from the object files corresponding to different source code modules contain information about address where each instruction needs to be placed in the program memory. Now, this system is doing it for you. All right. So a software utility that is now called the object to XI converter will now translate the absolute object file into the corresponding X or binary file. All right. And that is what the machine uses. That is what the machine understands. That's the machine code. All right. So it is that machine code now that you can now dump into the memory of your system, embedded system that you are designing. Okay. So next we look at the advantages of using the high level language option. Okay. So number one advantage is the advantage of reduced development time. Why is it reduced? Because the developer requires less or little knowledge on the internal hardware details and architecture of the target processor. So the major thing that he needs to know now, even though he has to have the knowledge of the registers, but the major thing is the ports. All right. That is the pins of the microcontroller, where you can now say send high here or send low there. All right. So the basic program that we'll be writing is to say for this, if this thing is connected to a switch, Oh, sorry. If we want to connect a switch, can use a pull-up resistor. Connect this other one to ground. Connect this to this. So if we want to use this, we can now say initialize this particular point to 0, all right, such that when we press the key here, that is the button, it is going to send, this is VCC, it's going to send a high to this place, all right. So that is the basic knowledge you are going to be having about the controller at this point in time. So you see that for each of them, you understand the pins, where the input pins are, the output pins, the pins that are ADCs and DACs, and so on and so forth. When you understand each of them, you can easily write a code that can be used to control the controller, right? That can be used to give life to your embedded hardware, your embedded system. Okay. So it is developer independent. It is developer independent. All right. So it is developer independent. Okay. So the syntax used by most of the high-level languages are universal, and a program written in high level can easily be understood by a second person. Okay. It can easily be understood by a second person. All right. Excuse me. Sorry, I'm having this disturbance here. Okay. Then another thing is portability. Well, what is portability? An application written in a high-level language for a particular target processor or controller can be easily be converted to another target processor or controller-specific application with little or less effort. In other words, we can easily make adjustments, and then it will work for another processor. So we've talked about the disadvantages now. What are the disadvantages? Number one, the cross compilers may not be efficient in generating the optimized target processor specific instruction. All right, may not do that very correctly. Number two is that the test images created by such compilers may be messy and non-optimized in terms of performance as well as code size. Okay. So number three is that the investment required for high-level language-based development tools is high, compared to the assembly language-based firmware development tool. Okay, so these are the basic disadvantages. But if you're able to overcome this, then you're good to go using high-level language development option. Right. So next, we look at the option of mixing of assembly language with high-level language. Number one, embedded firmware development may require the mixing of assembly language with high-level languages, or vice versa, especially in the area of interrupt handling. All right, source code is already available in high-level language, and then assembly language can be used in that area. Okay. All right. So the next is high-level language and low-level language can be mixed in three different ways. One, mixing assembly language with high-level language like C, mixing high-level language like C with assembly language, and then inline assembly. The passing of parameters and return values may be return values between the high-level and low-level language may be cross-compiler, or rather is cross-compiler specific. Okay, so assembly language with C. Okay, so assembly routines are mixed with C in situations where the entire program is written in C and the cross compiler in use do not have built-in support for implementing certain features like interrupt requests. Okay, so if the programmer wants to take advantage of the speed of the optimized code offered by the machine code generated by hand that's written assembly, rather than the cross-compiler generated code, okay, for accessing certain level, low-level hardware. The timing specifications may be very, very critical, and the cross-compiler generated machine code may not be able to offer the required time specification accurately. So writing the hardware peripheral across hardware peripheral access routine in processor or controller specific language and evoking it from C is the most advised method. All right. So in a situation where there are some certain things that you need to do, and then you are finding out that the cross compiler will not be very effective in actually dealing with that situation. For instance, when you are needing the execution speed, the performance of your of the embedded system to work better, when you are needing it, it will be better for you to actually embed assembly inside of your C code so as to get that particular speed that you desire. All right. Then you can as well, the same way you can still mix C with assembly. So there, the source file, you can still mix C with assembly and say that the source code is already available in this place. The source code is already available in assembly language, and routine is written in a high level language that needs to be included to the existing code. So the entire source code is planned in assembly in this method. Is planned in assembly, okay, for various reasons like optimized code, optimal performance, efficient code, memory utilization, and proven expertise in handling assembly. So the functions now written in C will use parameter passing to the functions and return values to the calling functions. So here the programmer must be aware of how parameters are passed to the function and how values return from the functions and is invoked from the assembly language environment. Now you are going to be writing some of your routines or functions in C, but there has to be an understanding on how to call those functions, all right, into the assembly environment. All right. So passing parameter to the function and returning values from the function using CPU registers, stack, memory, and fixed are most of the things that you have to be aware of. So its implementation is cross-compiler dependent and varies across compiler in this area again. Okay. So finally, we talk about the inline assembly. Okay. So inline assembly is actually another technique for inserting the target controller specific assembly instruction at any location of source code written in high level language C. So inline assembly will avoid delay in calling an assembly routine from a C code. So special keywords are used to indicate the start and the end of instructions, assembly instructions. So if you are using inline assembly inside of your C, at that point you are going to be using this to indicate where your assembly. If you are coding in PHP, you may understand what I mean, that inside of your HTML files you can bury PHP code. That's just the same approach here. So at that point, for instance, if you're writing PHP inside of your HTML, you simply write PHP and then your code, and then you also write this. So this same thing is just like here, you want to bury this inside of your code. Okay, so you are going to use this to open your code and then use this to close. So in between this that says beginning, all right, and then this one is the ending. In between this and this, you place your assembly, and you understand this. It says, and just like we say, this is the opcode and this is the operand, and this is moved into the accumulator register of 8051. This data in hex, this is actually a hex file because of this x hexadecimal value. All right, move it into the accumulator register. All right. Okay, so CAS-51 uses the keywords. That's if you want to do this using this particular IDE. Says that it uses these keywords and these keywords to indicate a block of code that you write in assembly. Okay, so that is it. That's basically it for embedded firmware design. All right. You remember to post your questions. You can send it through my email, and then I'll be glad to give you answer as much as I can. Okay, so thank you very much. In the next lecture, I'll see you. What's the next lecture, sir? Okay, don't worry. Next lecture we'll see. Next class.